All right, so let's start with reading number 14, and that's common univariate random variable. So again, a discussion on the random variable that is still going on, and we are talking about the univariate. That means one random variable, okay? And we're going to be checking about the distributions or the different shapes that the random variables can take. All right, so let's look at the first learning objective. Distinguish the key properties and identify the common occurrences of the distributions. Now, the distributions, there are a lot of distributions, but for the purposes of this particular chapter, we're going to just looking at 9 or 10. Okay, let's look at the definition. So discrete random variable is something that we've already seen. That's something that you can count. Okay, that's discrete random variable. So a distribution, if we create from a discrete random variable, we say that, okay, that's a discrete distribution. What about a continuous? These distributions take values in a specified range. We know for a fact that continuous, you cannot have a single value in a distribution. You always calculate within a particular range. All right, moving on to the distributions that we have. The first one is the Bernoulli random variable. Now, this is something which will help you in the other distribution, which is the binomial. So Bernoulli, just know the property. That's it. That's all that you need to know. The application of Bernoulli is used in the binomial distribution. So what is a Bernoulli random variable? A random variable will be classified as a Bernoulli random variable if the random variable can only take two possible values. Okay, when you toss a coin, there are only two possible values, either heads or tails. So we can say that, okay, a coin toss is a Bernoulli random variable. What about the default of a bond? We can say that the bond can either default or it can survive. Only two possible outcomes, right? A company can either survive or file for bankruptcy. So when we have just two possible outcomes, we classify them as a Bernoulli random variable. Okay. And here the notation is like this. Okay. So there are some notations that you should know. This one is referred to as probability of success, and the 0 is referred to as a probability of failure. That is just the notation. Okay, so 1 means success. That means if you toss a coin and you wanted to find heads, so if when you toss it, if the heads comes, then we say that, okay, it's a success. That means it's a 1. If tail comes, then it's a failure. That means 0. Okay, so these are the notations. Now, the main thing that you need to understand from the Bernoulli is that this is how the PMF actually looks like visually. But main thing is the formula that we have, which is the mean and the variance. Okay, the mean is the probability, P is the probability of success. So if a corporate bond, if defaulting, the probability of default is, let's say, 0.7, then that is going to be the mean or the average, or which is the probability of success, which is P. Okay, so whatever the P is, that is going to be the mean. What about the variance? Variance is P, okay, the probability of success multiplied by the 1 minus P is what? 1 minus P is the probability of failure. Because we just have two outcomes. If success is 60%, failure has to be 40%, right? So that's what we have in the Bernoulli. Now, these are just the common notations that you will see somewhere else. Okay, so just make sure that you go through it. P is the probability of success. This lambda, it's the average values which you will use in the Poisson distribution. N is the number of trials or the number of things that we have. Okay, now let's look at the second distribution, which is a binomial. Now, binomial is a collection of Bernoulli random variables. So Bernoulli is just for one coin toss. But if you do it multiple times, the distribution that you end up with, okay, this particular distribution, that will be actually a binomial distribution. Okay, moving on from the coin toss example, let's say if I have maybe two bonds, not just one now, I have two bonds, and the probability of one bond defaulting is this. The probability of the second bond defaulting is probably no default, and the probability that both the two bonds they default, that's this probability. So for a bond, the outcome is the same. It's either default, no default. But when you have multiple bonds, then it's going to follow a binomial distribution, or maybe multiple loans for a bank. Okay, so when it's discrete, when there are few in numbers, that's something that you can follow a binomial distribution. And what is the binomial distribution actually used for? It's used for finding the exact number of success, the exact number of times, the exactly how can, if you toss a coin or if you just roll a dice, what is the probability that exactly this thing will happen, exactly that thing will happen? So when you have something like that, we use the binomial distribution. Okay, and let me tell you, this Bernoulli, binomial, and the Poisson, these three distributions that we have in the book, they are all discrete random variables. So random variable which is discrete in nature will take either Bernoulli, binomial, or the Poisson distribution. Fair enough. And as you can see from the diagram, the bond default or any other thing can take on specific values, which is the speciality of the discrete random variable. Just hold on. Okay. I think this is fine. So as I said, this is used for this. What about the formula? If you want to find the exact number of success, how can you find it? Well, there is a formula for this, and this is something that you need to remember. Okay, make sure that you remember this for the exam. Okay, this formula. So the probability to find the exact number of success, that is equal to the n factorial, n minus x multiplied by x factorial. So basically, if you want to find probability that x is equal to, when you roll a dice, x is equal to 5, exactly it should land upon 5, you need to know that, okay, in how many ways you can do that. So there are like, how many trials, the n is the number of trials. So how many trials are you doing it? Are you doing it 5 times, 4 times, 3 times? So you need to define your n. Okay, then n minus x, x is something that you want, which is 5. So n minus 5, then multiplied by x factorial. So this is also factorial. So x factorial is something which is the 5 factorial, something that you want. Okay, then multiplied by the probability of, this is p is the probability of success to the power x, 1 minus p to the power n minus x. Okay, we'll take one little example on demonstrating this thing. Okay, what about a mean? If you have a binomial distribution and the question says that, okay, find the mean for it, the mean is the number, the n, multiplied by the probability of success. The same like the p, over here we just have n. See, because as I said, binomial is a combination, collection of Bernoulli. So the mean and the variance, they are pretty much the same. Okay, we are repeating n times. That's why we have this n over here. So that's the mean and variance of the Bernoulli and the binomial distribution. What about a Poisson distribution? When do we use this kind of a distribution? A Poisson distribution is often used to model the occurrence of events over some period of time, provided, okay, make sure that you know it, given some average or expected values lambda. So in the question itself, you'll be given an average value of something that is happening, and then you need to find, okay, how many times it's gonna happen, or exactly at what how many times it's going to be happening. So that is something that you want to find. That's something when you use the Poisson distribution, given expected or the average value, which is the lambda. That is when you use the Poisson distribution. Okay. Then it's used for finding like how many number of defaults that may happen in a bond portfolio. Let's say I have a bond portfolio and I want to find how many bonds will default. I am an analyst. I have maybe 10, 20 portfolio of maybe 10, 20 bonds that I have. And I wish to find in a particular time frame, how many bonds will default, so that I can use the Poisson distribution and I can find that particular answer. Provided I'm given some average defaults. Okay. Similarly, we can also use the Poisson distribution, and this is something that you would see in your operational risk chapter as well, is that how many operational losses a company will face. I look at last year and I see that, okay, I have faced maybe 4 operational risk losses. There were like 4 losses on average in the last year. So using that average data, I can create a Poisson distribution and I can find that, okay, how many losses, the operational list losses, will I face this year? So, okay, so that's something that I can do with the Poisson distribution. So let's just look quickly at the example. Okay, and the formula for the Poisson distribution to find X success given some average values, you need to remember this particular formula, okay, which is the lambda, which is the average. Okay, this is the average multiplied by e to the power negative lambda, this negative average, and over here we have the x, which is something that we want to find, divided by x factorial. You use this formula and you get your X success, whatever that you need actually, using the Poisson distribution. Let's look at these 2 examples. Okay, so on average, let's say 5 bond defaults, they happen every year. Okay, you are managing a portfolio and you notice that 5 bonds, they default every single year. So this is the average. So once you hear this thing average, it clicks, okay, that it's a Poisson distribution. Then what is the probability that 3 bonds will default in the next period? Now you want to find the probability that 3 bonds default, probability that X is equal to 3. That's something that you want to find. And these are the questions that you would see on the exam. So what do you need? You have your average. Yes, the lambda is 5. Okay, replace, just use this particular formula. Okay, so I can, the lambda is 5 to the power x. X is something that 3 multiplied by e to the negative lambda is 5 divided by x factorial, which is 3 factorial. Once you solve this entire formula, you will have the answer, which is the probability that exactly 3 bonds will default in the next period. Okay, and then what is the average default? If this is the question, what is the average default? The average is already 5, which is the mean. Over here, it's lambda. The variance, it's also lambda. Same, 5. No variation at all. Okay, so only thing, make sure that you do remember this formula for the exam. Let's take the second one. Assume we have 4 bonds now, or maybe 4 customers, 4 loans, whatever that you want to say. Okay, and an analyst wants to find the probability that exactly 3 bonds will default. What exactly you want? 3. So put it out here. Probability that X is equal to 3. With probability of each bond defaulting is 10%. Now there is no average bonds here. So now you know that, okay, it's a discrete number because we want to find the probability to be exactly 3. So we need to use the binomial distribution. So probability that exactly 3 bonds will default, okay, that is going to be this particular formula. So what is n? N is the number of things that we have. N is equal to 4. What is x? X is something that you want to find exactly 3. So that x is equal to 3. Is there any probability? Do we need the probability? Yes, we do need it. And it's going to be mentioned on the exam. The probability of default, the P is 10%, which is 0.1. Now just plug in the formula and you have your answer. Okay, so as an example, all we can do is probability that exactly 3 bonds will default, that is equal to n is what? 4 factorial. Then n minus x is 1 factorial, and then x is 3 factorial. Multiplied by probability is 0. Probability of success to the power x. X is what? 3. Multiplied by probability of failure, that this is success, this is failure, right? 1 minus p is 0.9. 1 minus this thing to the power n minus x. What is n? And 4 minus 3, that's 1. So once I solve this thing, 4 into this 4 factorial, you just take this thing. Okay, you can use a calculator, you can solve it. 1 factorial is 1, 3 into 2 into 1. So this is gone. So the answer that remains is 4. Okay, so that's going to be 4 into this 0.1 times 3 into 0.9 times 1. So once you solve this thing, you will have your probability that x will default. There's going to be 3 defaults, exactly 3 defaults given this sort of data. Okay, so it's very simplistic. Do not get confused with these distributions. They are very simple. All you need to do is that you need to remember these formulas and just look at the question. Everything is there. You can easily solve these questions if they occur on the exam. Okay, so make sure that you are thoroughly with that. Okay, now from the discrete, we are moving on to the continuous distribution types. So the very first continuous distribution is the uniform, okay, continuous uniform distribution. So it's a distribution where each outcome is equally likely to occur. So maybe a probability of default, if it's continuous and each bond or each loan has a, equal probability of default or something like that, then we say that, okay, it's a continuous uniform distribution. Similarly, the probability of a rolling a dice is 1/6. So 1/6 for all the things. But remember, we are doing continuous. Okay, so that means having a single value, the probability of x is equal to a single value, let's say 2, that's going to be 0 because it's a continuous. You cannot have a single value. Okay, so the probability, having a look at this thing, this yellow rectangle is a continuous uniform distribution. It's bounded by A and B. That means, above this B, there's not going to be any probability, and below this A, there's not going to be any probability. All the probabilities is going to be within this yellow rectangle. Fair enough. And if you want to find the probability, as I said, it's always going to be within a range. In a continuous, it's always going to be within a range. So let's say A is 10, this B is, let's say, 20, and this X1 is, let's say, 15, and this X2 is, let's say, 18. And you want to find the probability within this. This is something that you want to find within a range, like between 15 and 18. What is the probability for that? Well, it's very simple. X2 minus X1, that is 18 minus 15. You take the difference divided by the overall probability that we have, 20 minus 10. You solve this thing, 3 over 10, that's going to be 30%. So this probability that the random variable will be between 15 and 18 is going to be 30%. A very simple, out of all the distributions, this is a very simplistic one. All we are doing is using this particular thing, and we can find any value within this range, even though it's a continuous distribution. Okay, so talking about the mean and the variance, mean, as you can see, it's very simple. It's the simple average. I mean, of course, if this entire thing is 100%, if you divide it in the middle, then it's going to be the mean or the mu, right? So formally, it's a plus b divided by 2. That's this value divided by 2, and you get your center point, which is the mean. What about the variance? Variance is b minus a square, this minus this, square it, divided by 12. Okay, this is something that is there for variance. Okay, the more important formula is this. This is something that you need to know for the exam. All right, so that's the continuous uniform distribution. What about the normal distribution now? It's a very crucial something that you would see in finance and throughout the FRM curriculum a lot is the normal distribution. Also, we call this as a Gaussian distribution. Now, when we talk about normal distribution, if you look at this distribution, this shape, it's a bell kind of a shape. It is symmetrical. That means by just having a look, visual look, I can say that yes, it's very identical. It's symmetrical. Whatever that I have here is something that I have here as well, right? So it's symmetrical in shape. The mean, median, and mode are all equal. So if I just take this center point of this distribution, that's where I will have my mean, which is expected value of x is mean. I will also have my median and my mode, because mode is the, the top value, which is this. The median is divides into two parts. So that's the median as well. So that's one thing that we have for normal distribution. The mean, median, and mode are all equal. The skewness is 0. As you can see, there is no skewness left, right. No, there's no skewness at all. So that's a 0 skewness. And the kurtosis is 3. Okay, remember this for the exam. A normal distribution has a kurtosis value of 3. And then by looking at this normal distribution, we say that, okay, when we look at the kurtosis, we say that, okay, it's above, less. That's different topic. But for this, remember kurtosis is equal to 3. Now, let's talk about the first thing that we have over here. It's a first normal distribution. Now, the best thing about normal distribution is that most of your data, okay, when you work in finance, when you have data, most of the data, they will look like a normal distribution. So that really helps you as an analyst. It really helps us to understand our data in a much better way. Okay, so if my data is like this, by just having a look at it, I can say that, okay, 50% of my values is to the left of the mean. This is mean, right? And 50% of my data is to the right of my mean, the average. I can do that. Moreover, by looking at the normal distribution, there are some established features, which is like this: within one standard deviations away, like this, one standard deviation away from the mean, there's going to be 68% of the data. So if I'm doing a research, I can say that yes, 68% of the data is within one standard deviation from the mean. So I can conclude certain things. Moreover, I can say that within 2 standard deviations away from the mean, I have almost 95% of my data values. That's also a good thing. So this establishment, okay, this within one standard deviation, within 2 standards, it's known as confidence intervals. Okay, that's my confidence interval. And basically I've taken an interval of within 1 standard deviations, within 2 standard deviations away, and so on and so forth. So it's a good thing. If I have a data, it looks like a normal distribution. I can just go ahead and I can make some conclusions. Okay, let's try to do that for this particular data that we have as sales data. Let's say I'm looking at the sales of my company and I see that, okay, this $20 million is my mu, or the average. And then I want to make some conclusions that, okay, What is my sales? The average sales is $20 million. Okay, fair enough. Then how likely is it that the sale is going to be within one standard deviations, that is between 16 and let's say 25, whatever that number. So I can say that, okay, the probability is 68%. 68% of the times it's going to be between 16 and 28. I can say that by just having a look at this confidence interval. But now let's be more specific. Okay. And I want to find what is the probability that, okay, it's going, my sales is going to be $32 million and above. $32 million and above. I want to find that. So now this is a challenging part. I can use this, but it just gives me pretty much 68%, 95%, so on and so forth. But I want to be very specific. Okay, like I want to know what is the probability which is beyond 32. So in this case, what I need to do is I need to convert my sales data, which is a normally distributed, into something which is what we call as a standard normal distribution. Okay, so a standard normal distribution, once I convert this, the mean will be 0 and the standard deviations will be 1. So the difference is going to be 1 standard deviation. Over here we have 1 standard deviation, 1 standard deviation, so on and so forth. That's the benefit. Here we have a different standard deviations. 20 minus 24, that's 4 standard deviations. 16 minus 20 minus 16, that's -4, so on and so forth. So here the standard deviations is different. If you have another data, maybe revenue, other kind of data, any company data, the standard deviations will be different. So the best part about a standard normal distribution is the mean is always 0 and standard deviation is always going to be 1. Now, you must be wondering, like, what's the use of converting this thing? Well, if you have a standard normal distribution, any data, any probability or any value that you want to find under the curve, you can find that with the help of something which is what we call as a Z tables. You look at the Z tables and you can find any area under the curve. And that is the best part of converting a normal distributed into a standard normal distribution. Now, how do you do that? You use this particular formula, which is the Z value is something that you need to calculate. Okay, so that's X minus the mu divided by the standard deviation. So let's say the X is what? X is, let's say, any value. Let's say I want to find above 32. That was something that I wanted to find, right? So I can take the X as 32. This mu is the average. The average is the center point, which is 20. Standard deviation, as we calculated, it's 4 standard deviations. So once I solve this thing, okay, 12 divided by 4, okay, and that's going to be 3. So Z value is equal to 3. So I get my Z value, which is equal to 3. So after solving this thing, I've converted everything and I got a Z value over here for 3. Now, what do I need to find? I need to find the area over here, which is this one. So how do I find it? I'll go to the Z tables and I'll find where do I see this 3, and that's going to be my overall value. Okay, so let's just go to that. Okay, so all right, so this is the positive or the cumulative Z table that is going to be provided to you on the exam as well, and something that you will have. So you don't need to remember these probabilities. Everything is going to be provided on the exam. So now how do you look or how do you check on the Z table? So first thing to notice is this thing. As you can see, it's a cumulative positive table. All the values are positive. There are no negative values of possible that is here. Okay, and it's also known as a left tail probability. That means this blue thing, as you see here, is all that is there in the center. These centers are all the probabilities. Okay, now we wanted to find that, okay, how much was above 32, the probability that my X will be greater than 32. That's something that we wanted to find, right? So we calculated the Z value and it came to be 3. Now, just look on the Z values over here. Just look at the value of 3. Let's just check, where do we see 3? So it's not there actually, it's 2.9, but there is also a 3. For this example, let's just say that we calculated the Z value to be, let's say 2.95. Okay, let's just say that. So 2.95, I can search for 2.95. So 2.9 and then 5. Okay, this one, 2.9 and then this. Okay, so this is going to be, sorry, this one, 0.9984. So Z value for 2.95, looking at the table, it came to me that, okay, this is 2.9 and from this line, it's 0.9984. But this is giving me the value for this one, right? It's giving me the value for this one because this table is meant to give you the values for the left side of the distribution, all the left side. Okay, but I wanted to find the right side, which is this one. I wanted to find the right side, but the table is showing me the left side. So it's very simple. How do you do it? Well, we know that the entire distribution is 100%. That is 1. So I can just take this value 1 minus 0.9984 and I can find maybe whatever the answer that I get, that is going to be my probability for the right side. Okay, so if you want to find the right side, just take 1 minus the value that you get. That's it. Okay, so this is simplistically how you go ahead and you find the value on the right side.
Sir, I have one question over here. Like, how we are going to identify that, they are asking for a right or a left side? Like you mentioned over here, right, that we will subtract 1 when the value will be asked of the right side.
So yeah, so this thing is something that you would see on the exam, and it's going to be mentioned as a left tail probability or Z is less than. So this blue sign that you see here, this entire blue curve that's been shaded, okay, this means that all the Z values that you have, they are to the left. That means it's a left tail probability. So all the values, all these values, okay, inside the table that you see, all these values are to the left of the Z tables or to the left of the distribution. That is what these things tell. So if you want to find this white region over here, you cannot find using this table. Why? Because there are no, I mean, all the probabilities are to the left and you want to find to the probability to the right. Like for example, in our example, we wanted to find the probability to this side. This one we wanted to find, right? Probability X is greater than 32. Greater. That means 32, 33, 34, 35, so on and so forth. So we wanted to find the probability for that. But here we have a table which is giving me all the probabilities to the left of it, which is less than 32. But do you want to find less than 32? No. I want to find greater. This region I want to find. So if I have the probability from this table, I can find the probability which is less than 32 was 95%. But I wanted to find the greater. So of course it has to be 5%, right? This entire distribution is 100%. And if you find this region, okay, if you find this region to be 95%, so the other has to be 5%. So that's the reason why we take 1 minus 0.95. All right, so that's why we convert every data into a standard normal distribution so that we can find any values that as an analyst we are interested in. All we need to do is we need to use this particular formula. Now, what are the benefits of standard normal distribution? Well, the first thing is that the mean is 0 the standard deviation is equal to 1. As I said, that's the standard property. And you can find any value under the standard normal distribution with the help of Z tables. And what are the steps for that? Well, first convert your normal distribution to the standard normal by using that Z formula. That's something that we have seen. Once you get your Z value, go to the Z table and search for the probabilities. Then make sure that the table provided on the exam will most likely be a positive cumulative, which is what we saw. But since it's a normal distribution, negative value probabilities will be equal to the positive value probabilities. That means if you want to find this region, no problems at all. Just find the positive one and replace the sign. That's it. Put a negative sign in front of it. That's it. Okay. That's the normal distribution, standard normal distribution, I would say. Now, moving on to the other distribution that we have, and that is the log normal distribution. Now, there are times that normal distribution cannot be used everywhere. For example, if you have a stock, let's say ABC company, if you're, taking the historical data of all the prices, do you think so it's going to follow a normal distribution wherein it's going to have negative values like maybe negative 70, negative 50, so on and so forth? Can any company or a stock price can take negative values? No. So at those times, normal distribution cannot be used. So an alternative is a log normal distribution. Okay, so when your X, all the numbers are a negative number, you can take a log of that using this thing, and you get a distribution which is what we call a log normal distribution. Okay, so what are the properties of log normal distribution? It always has positive values. So good. I mean, if you want to model your stock prices, we know that stock prices, they can take positive values. The lowest it can go is 0, not below that, right? And what about the log normal distribution? Second property, it's bounded by 0. As you can see from this particular thing, it's the max, the lowest value it can take is 0. And it's right skewed. That means this tail is going on and on to the right. So it's a right skewed distribution. What are the uses of log normal distribution? As I said, stock prices, that's a very first usage. Modeling the stock prices, because we know for a fact that stock prices cannot take negative values. Second thing, in your operational risk chapter, you would see that, okay, log normal distribution is used to understand or to find out how much is the risk loss, operational risk loss amount. How much is my amount? Okay, so that's when we use the log normal distribution. I've put this here so that when you go to that chapter, this thing, you're going to come back to this thing over here as well. So it's better that you know that, okay, if you want to model operational risk loss severity is something that you would see over there. Loss severity, how severe or how much you use a log normal distribution for that. Okay, and as it's a right skewed, that means the loss is how much? Maximum loss. What's the maximum loss? That's a log normal distribution. All right, moving on from log normal to something that we have, and that's the T distribution, the chi-squared, and the F distribution. Have a look at this particular table that I created. A T distribution, it's pretty much like a bell-shaped curve, similar to normal distribution. But remember, it's not exactly a normal distribution. The reason is that it has got a lot of fat tails. The tails are pretty much fat. And that is the difference between the T and the normal distribution. And all the distribution that you see in this line, T, chi-squared, F, they are used in hypothesis testing. Okay, but let's just go through it. So a T distribution, it has got a lot of fat tail. Let's look at the properties. It's similar to the normal distribution. Okay, fair enough. It has fat tails. Okay, it has degrees of freedom. Okay, now there's a concept of degrees of freedom, which is actually used in the hypothesis testing. But for now, do not get into the, if you don't know what that is, it's just a freedom that is allowed if we have 10 variables or 10 things. All, let's say if there are like 10 people, 10 chair. Okay, 9 people out of those 10, 9 people have a choice to pick up the first chair, second chair, third, fourth, fifth, sixth, 7, 8, 9, 10. But the last person who's remaining, he doesn't have a choice. If all the chairs are gone, he's just left out with only one chair that is left. So he doesn't have a freedom at all. So with data as well, we use something which is known as degrees of freedom. And we say that, okay, if there are 10 people, 10 numbers, use 9 values, n minus 1. N minus 1. So if there are 10, the overall freedom is only to the 9 people, as I gave you the example of chair. So that's the degrees of freedom concept. Okay, so it's similar to normal distribution, has fat tails, has degrees of freedom, which is n minus 1. And as the degrees of freedom approaches, or as the degrees of freedom increases, as the n increases, the T distribution, it approaches to be a normal distribution. Okay, so if you just see this blue line here, it's got a pretty much fat tail over here, a lot of fat tails, because the degrees of freedom is dependent on n, right? So if the n is low, the degrees of freedom will be low. So as the degrees of freedom is low, it's going to be looking like this. But as the degrees of freedom goes up, it's going to look pretty much like a normal distribution. Okay, so that is something that you need to know, what degrees of freedom. And as the degrees of freedom increases, degrees of freedom means number increases, it's going to look pretty much like a normal distribution. What about a chi-squared distribution? Not very much talk in the overall FRM part 1, but it's used to test if variance of a normally distributed population is equal to some value. Okay, so it's used pretty much in hypothesis, but as I said, not very much used in the FRM level 1. So just know that, okay, it is used to test the variance of a population to some sort of a value. So variance of a population, maybe you're saying that, okay, it's equal to 20. You're saying that, okay, you have a population data and you're saying the variance of that data is going to be 20. That's your assumption. That's your hypothesis. So then you use the chi-squared distribution for that. But more important, what are the properties of chi-squared? It's again bounded by 0. It's asymmetrical in shape. As you can see, there is asymmetry, just like a log normal distribution. And it also approaches a normal distribution as degrees of freedom increases. As the data increases, degrees of freedom increases, the chi-square will look like a normal distribution. Fair enough. What about the F distribution? Now, this is something that you would see a lot in the hypothesis in the multiple regression chapter. Okay, so what is an F distribution? It's used to compare equality of two variances of two populations. When you have two population, let's say CFA candidates, FRM candidates, and you want to compare the variance of both these two different populations, then you use the F distribution for that. But moreover, this F distribution in FRM part 1, it's going to be used a lot in multiple regression hypothesis testing. That is the betas, all those betas coefficients that we have. We want to test that. Then we use the F distribution for that. Properties of F distribution: bounded by 0, yes. Right skewed, yes. Numerator has degrees of freedom. Denominator also has separate degrees of freedom. So this is a special thing. If you look at the formula of the F distribution, okay, the numerator, whatever we have in the numerator and whatever we have in the denominator, this will have its own degrees of freedom and this will have its own degrees of freedom. So just like a Z table that we saw, we also have an F distribution table. And on the table, you will see numerator degrees of freedom, denominator degrees of freedom. We'll look this when we are doing the hypothesis testing. Okay, so that's what we have within these three distribution. Then we have something known as the exponential distribution. It's exponential is used to model the waiting times, that how long, if I go to a restaurant, how much will I have to wait? Okay, how much time will I have to wait for that? So that's using an exponential distribution. I can use that. Or also in talking about the finance example, it's like how much time it takes for a company to default. Let's say I've invested in a particular company and I want to find out how much time will that company take to default. I can use an exponential distribution for that. Or maybe if I want to find that, okay, a startup company has given a bond, how long or how much time will it take for that company to default, or for that bond issue to default? I can use an exponential distribution for that. Okay, so make sure that you just know that why do we use the exponential? That's all that you should know. Okay, moving on to the beta distribution. Again, this is something that you just need to know these two lines. That's it. This distribution can be used for modeling default probabilities and recovery rates. Okay, when you look at your credit risk data, if you want to find probabilities of default and so on and so forth, you can use a beta distribution for that. If you want to find recovery rates, a bank has given a loan to the borrower and the bank wants to find how much they can recover, they can use a beta distribution for that. Okay, so it's used in credit risk modeling. What about a final thing that we have, the final learning objective, and that is a mixture distributions. So here, two separate distributions are combined. Okay, let's say that you have a data, you have two distributions. Maybe this is something that is one and this is something that you have two. So you can actually, you can mix it up, these two distributions, and you can form a better distribution, a final third one like this. Okay, that's going to be a mixture distribution, a combination of two distributions that we have seen so far. That's a mixture distribution. Let me tell you, there are almost like 100 different distributions that are available. So you can combine any one of them and you can get your, so that it fits your data very well. That's the overall objective. Now, mixture distribution, it contains elements of both parametric. Parametric means the mean and the variance, which is like a normal distribution, and non-parametric, which is like just the historical data that you take. Okay, so when you have a mixture distribution, it's going to have parametric as well as non-parametric. What is parametric? Like all the distribution that we have seen, the normal distribution, it has a mean, parameters, variance, which is another parameter. Non-parametric, like it can be historical data distributions. Okay, when you just have the historical, you just pull it up, that's it. However it looks like, your data, however it looks like, it doesn't make any difference. Okay, then the usage of mixture is that we can see, or we can actually change the skewness and kurtosis of our data with mixing of distribution. So if our data is very much skewed, we can change it when we mix the distribution. That's all that you need to know for mixture distribution.